Good morning all. Welcome to the webinar. And as you can see on the screen, today's webinar is on Floating Point PID control in Cscape IEC Editor. We'll go to the presentation first. And if you have any questions, please type in the question box and we'll address them at the end of presentation. Thank you again. Let's start with the presentation.
Hello and welcome to today's webinar. Today we're going to be looking at Floating Point PID control in Cscape's IEC Editor. Let's get started. Let's look at our agenda for today. We'll start with a quick review of PID control and the Horner Advanced Ladder PID instruction because the way it operates is perfectly applicable to today's topic. We'll also spend some time detailing what you need to know for using PID with our IEC languages, specifically the Floating Point PID instruction. There will be demonstrations throughout and we'll finish with a Q&A session. PID is a mathematical method process control with a history spanning over 100 years. This method involves three key parts: a proportional component, an integral component, and a derivative component. We'll look at these in more detail shortly. In practice, PID is the most widely used algorithm for managing various processes, such as temperature regulation or pressure control. Don't get overwhelmed by the mathematical equations or symbols on this slide. The critical factor for successful process control is understanding your specific process and its dynamics. What are you trying to control? What influences it? And so on. This understanding is far more crucial than the intricate mathematical details. Now we'll examine some elements of the PID algorithm. When we're engaged in process control, we're usually dealing with a specific process variable that we aim to manage. For example, if we consider a pizza oven. With a pizza oven, our focus is usually on controlling temperature. Let's say we want to maintain it at 480 degrees Celsius. This 480 degrees represents the set point for our pizza oven shown on the far left. Now, the method used to control temperature depends on the type of pizza oven. An electric pizza oven might toggle an electric heater on and off, while a gas pizza oven could manage temperature by regulating a proportional valve to adjust gas flow. Whatever we use to control the process variable is referred to as the control variable. The controller effectively manipulates this control variable to influence the process as we measure and manage the process variable. We offer two variations of PID algorithm, an independent algorithm and an ISA algorithm. While they have some differences, either one works well for most applications. Both of these instructions in our advanced ladder editor use integer-based math. Integer math can be very effective for PID calculations. For each PID loop, it's a requirement to allocate a 16-word control block. If you opt for auto-tuning your process, you can choose either an independent or ISA loop with auto-tuning. When we auto-tune our PID loops, we use the Ziegler-Nichols open loop method, which is a commonly used algorithm for tuning PID loops automatically. We'll look at this in more detail later. Another feature of our PID instructions is their ability to support both digital and analog control variables. So whether you need to rapidly turn something on and off like a heater, digital control variable, or gradually adjust something like a proportional valve, analog control variable, our PID instructions can handle both scenarios. We mentioned that every Horner PID instruction requires a 16-word control block. The first few words of this block are used to set up the PID instruction for your specific application. This setup includes defining parameters like the sample period, dead bands, the acceptable range below the set point, and the coefficients for proportional, integral, and derivative control. There are additional parameters like upper and tops, which define the highest and lowest values your control variable can reach during the process control. There are several other parameters, but these are the key highlights. One of those 16 words is a control word or config word, which we use to set the parameters. This includes how the error term operates, such as whether it's the set point minus our process variable or the reverse, and the output polarity, positive or negative, of our process. In most cases, you can leave these parameters at their default settings, but it's essential to be aware of their existence. Now we'll go back to the auto-tuning process. First and foremost, auto-tuning isn't a universal solution for all applications. In fact, for many applications, auto-tuning isn't effective. In such cases, a manual approach is necessary to achieve a better or quicker tune, or sometimes a manual approach is the only viable option. Ziegler and Nichols were scientists who developed a set of algorithms in the 1940s for tuning PID loops. They devised both an open loop and a closed loop method, and we're focusing on the open loop method here. When you enable auto-tuning in a Horner OCS PID loop, it initiates a specific procedure. It immediately sets the control variable to its maximum value, which is determined by the CV clamp, and turns it up until the process variable surpasses the set point. Once that happens, it turns the control variable all the way down until the process variable drops below the set point. This cycle repeats 3 times. Throughout these cycles, the system records timings and values. After completing the 3 cycles, it uses these timings and values in the algorithms shown at the bottom right to determine the optimal proportional, integral, and derivative coefficients. This is how auto-tuning works in a Horner product with the Ziegler-Nichols method. Now we'll look at the specifics. Everything we've discussed so far applies to IEC as well. In IEC, you not only have integer type loops like independent and ISA, but also floating point versions of these algorithms. Just like in advanced ladder, you can also use these in auto-tuning modes, providing you with more flexibility. You can opt for an integer-based or a floating point approach, both of which are highly effective. Now we'll examine one of the floating point PID instructions available in Cscape for our controller. On the screen is a screenshot in function block diagram format. In IEC and PID, you can choose from multiple languages, including structured text, ladder, or function block diagram. The instruction on the screen has various inputs. The first input is the control block, which is an array of 16 integers used to set up the PID block. We'll look at this shortly. You also need to provide the set point and the process variable, both as real values. There are inputs for manual control. When implementing PID control, it's essential to keep the PID algorithm connected to power, ensuring continuous execution. We might want manual control of the process without turning off the PID loop. Instead, we switch the PID loop to manual mode using digital variables. We also have inputs for auto-tuning and outputs to signal when auto-tuning is complete. In IEC, there's a unique input, the precision variable, which is a real value. This specifies the precision for floating point values in the algorithm, often set at 0.01 initially. On the output side, there's an auto-tune done bit and the control variable, which is the PID loop's output. Unlike Advanced Ladder, you can't write directly to the control block in IEC. Instead, we use the set PID instruction available in both integer and floating point versions. It allows you to configure parameters like sample period, dead bands, coefficients, and clamps. In manual control, we don't directly set the control variable value within the PID instruction. There's another instruction for this purpose in IEC. You activate a bit to put the loop in manual mode, and this instruction lets you set the specific control variable manually. Don't forget to set the precision for this loop as well. Today we'll demonstrate how to set up PID in IEC using Cscape and a practical example. In this setup, we're using an XL4 controller and programming in Cscape, with the core of the program utilizing a PID algorithm in a function block diagram. Our input, representing the process variable, is temperature, while the control variable involves a light bulb for heating. The output is a 4 to 20 milliamp analog signal. To achieve on/off control of the light bulb, we've incorporated an external proportional power regulator. Additionally, we have a thermocouple providing feedback for temperature sensing. In our demonstration, we prefer using function block diagrams for IEC process control, although ladder and structured text are available options. To begin, we'll locate the PID instruction in the toolbox. We have two categories, PID for integer-based instructions and floating PID for the floating point version. For this example, we've selected an independent auto-tuning floating point version. Once you drop the PID instruction onto your desktop, you need to give it a name. We named ours temp loop, and it functions like a variable in the variable table. Now it's a matter of connecting the inputs and outputs for your specific application. Firstly, you'll need to allocate a control block, in this case, an array of 16 integers named temp loop CB. In IEC, it's crucial to avoid syntax errors. When you encounter inputs with brackets, it typically means you shouldn't include the array index like temp loop CB bracket 0. Just use the array variable name without the index to prevent errors. Now we'll look at our PID setup. We input the control block as the first parameter. Then we use floating point variables for the setpoint and process variable like temperature for pizza. We include manual inputs for toggling manual mode and adjusting the control variable or CV. Additionally, we have auto-tune variables, a Boolean bit for auto-tune mode, and settings for filter, responsiveness, and tuning type. These settings use defined constants, which you can find in the help file under PID instructions. It's all about precision and accuracy in configuring your PID control. This is the PID instruction we're using. However, as we mentioned earlier, for configuring the PID, you'll need another instruction called set PID. This instruction fine-tunes the PID algorithm's operation. You must reference the same control block to ensure it's for the same loop. We set the period in 10 millisecond increments for resolving the PID equation. In this case, it's set to 3, so we recalculate every 30 milliseconds. Although there are dead band settings, we won't use them. You'll configure variables for your proportional, integral, and derivative coefficients. One frequently overlooked is the CV upper clamp, which is crucial. Don't forget to set your control variable's upper clamp and adjust other parameters, which are detailed in the help file and discussed in the slides. Looking at the input side of our setup, we're using a temperature sensor with an XL4 equipped with Model 5 I/O. This provides built-in analog inputs, and we're employing a thermocouple as our input source, reporting values in 20th degree increments. These values are fed into analog input register AI1 as integers. If we want to control our process in degrees Fahrenheit, we need a floating point variable in Fahrenheit as our process variable. To achieve this, we take the temperature input, represented by %AI1, convert it to a real value and scale it to shift from 20th degrees Celsius to 2 degrees Fahrenheit. We use the Celsius freezing and boiling points, 0 degrees Celsius and 100 degrees Celsius, which correspond to 32 degrees Fahrenheit and 212 degrees Fahrenheit, to perform this conversion. The scaling accommodates the 20th degree increments in our input data. Now we'll look at additional logic before we see the bench. So here we have our manual control. So this bit here, which is temperature manual enable, when that's turned on, it will be in manual mode, which means we're going to be manually controlling the CV. So we need to do some scaling on our CV, which is a floating point value, and we need to scale that and convert it to an integer so that we can write it to our analog output value, which is tied to %AQ9. So what we're doing here is we're taking the raw value from our CV, we're multiplying it by 20 to expand the range and to take advantage of more of the range, and then we're converting it to an integer. But before we do that, we have this binary selection because the raw CV value that we need to scale could be coming from our PID loop as an automatic value, or it could be coming from our manual instruction here as well. So we have to select which of the two is being used at any given time based on the fact whether we're in manual mode or not. And we're going to scale each of those the same way by multiplying by 20 and converting them to an integer. So that's the logic we have here. So what we see here on the bench on the left is a small plastic enclosure with a light bulb in it. And you can see that light bulb is turning on and off. We have a separate component that's connected between the 4 to 20 milliamp loop and light bulb. To change that to a proportional on-off control, there's an extra component in there. On the face of our XL4, we can see our target set point. On the left, there is 90 degrees Fahrenheit, and our actual is on the right in degrees Fahrenheit also. And then on the screen, we can see that the PID algorithm's coefficients for proportional, integral and derivative terms, and we don't need the derivative terms because there's plenty of stability and overshoot is not a problem. Here we have the auto-tuning screen, which when we turn on the auto-tune button, brings us into that modified Ziegler-Nichols process. We'll run through the process 3 times up and over the set point. And then the OCS itself will then write the P, I and D coefficients that were a result of that experiment into coefficient terms. So that's how that works. And of course, when it's done with that experimental, the done bit will turn on. And then finally, there's a screen that can be used to manually control the CV. So when we turn the manual mode button from off to on, then we type in a manual CV that will process to go to that specific value, and then the automatic CV will be ignored at that point. So as we saw today, the PID instructions available for Cscape's IEC Editor are very like those available for Advanced Ladder. In addition to integer-based PID instructions, IEC also offers floating point-based PID instructions. It is important to keep in mind that in order to operate the PID loops, there will be a couple of other instructions to be aware of, one to manipulate and set up the control block, and another for actually the writing of manual values to the control variable. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Thank you all for tuning into the presentation. Well, I don't see any questions there, so we'll just quickly go through the next week webinars. So as you can see my screen, we covered the floating point PID control this week. So the next week is structured text math instructions in Cscape IEC Editor. Following that, we'll be reviewing Cscape Enhanced IEC Editor and for and while loops in Cscape IEC Editor, and as well as the more and little known system registers. So registration is open for all these webinars. I request you to register yourself and hope to see you next week. Thank you very much for joining. Thank you. Have a good day. Bye.